All right, in this video I want to walk through in a little bit more detail the problem that we were working on in the last video. So that was a non-isothermal PFR with multiple reactions. 2A goes back and forth to B, and 2B plus A goes to C with elementary rate laws. So this solution is posted to Canvas so you can look at it, but I'm going to walk through it. So basically the mole balances for each species, those we can just write down the PFR mole balances. Because we have multiple reactions, we have to account for the fact that the different species are being generated and or formed in the different reactions. So for example, the rate of A is going to have contributions from reactions 1 and 2 because A is involved in both. Same with B, and then C is only formed in reaction 2, so only has one term. So when I write these expressions here, I'm just going to start out by writing them. If it's A that I'm interested in, I'm going to write the rate of A for each reaction, even though they're given, for example, this reaction is given in terms of C, and I'm going to use relative rates next to convert to the right, or convert to the species that the rate is given in terms of. So that's what I'm doing here. So here we're saying the rate is given in terms of C, the rate of reaction 2 is given in terms of C, and the rate of reaction 1 is given in terms of A. So for the different species that are involved, I'm using the relative rates expression, which is equation 3-1 in Fogler, to make that conversion. So if you recall, that's the rate of the species in that particular reaction divided by the stoichiometric coefficient, where stoichiometric coefficients on reactants are negative and stoichiometric coefficients on products are positive. So if I get all of that information, now I can fill in the rates for the species that are not given. So for example, we aren't given an expression R2A, we're given R2C, but I can relate R2A and R2C via the stoichiometry or the expression of relative rates, which is what I'm doing here. Next, I'm going to do the energy balance. So again, we take this volume slice to do the energy balance on. Coming in, we have flow rates times enthalpies, specifically heats of formation. And coming out, we have flow rates times enthalpies, specifically heats of formation. And we're doing this over this infinitesimally small volume slice, starting at V and going to V plus delta V, where delta V is going to approach 0. So I'm going to write this out as a sum to save space. Sum of the flow rates times enthalpies coming in minus sum of the enthalpies times flow rates coming out, plus a heat exchanger term. So we're doing here the constant TA case. So UA times TA minus T times delta V. Next, I'm going to take this expression, divide by V, and take the limit as delta V goes to 0, and that is the definition of the derivative. So I get a ddV term, and since I have in minus out instead of out minus in, it's a negative ddV. So minus ddV times sum Fi times Hi plus this heat exchanger term. So recalling I need to use the product rule on this term, so I'm going to take the first times the derivative of the second plus the second times the derivative of the first. So that's what I've got right here. So Fi times dHi dV minus Hi times dFi dV plus the heat exchanger term. And then if we recall from the lecture where we derived energy balances for tubular reactors, we said we could turn this piece dHi dV into CPI times dTdV. And then we said this term, this dFi dV term, this is our mole balance. So dFi dV is going to be equal to Ri. So this term turns into Hi times Ri, and then our heat exchanger term here. So I want to show here that we can do this in two different ways. In the two different ways, basically we're going to take the second reaction and we're going to write it one time in terms of C, and we're going to write it the second time in terms of B. The reason we're making the choice between C and B is because the rate is given to us in terms of C, but the heat of reaction is given to us in terms of B. Because of stoichiometry, all we really need to do is convert in either case and get the same answer, but I want to show that here. So the first way, we're going to take the second reaction in terms of C. So this is basically expanding out this expression. So these are all of our dTdV times flow rate times heat capacity terms. So that's basically this expression expanded out. Now we have our enthalpy times rate term. So we're going to take this one species at a time. So here we have species I is equal to A. So I is equal to A. So we take HA and we multiply that by the rate of A. The rate of A, I can go back up here and I say the rate of A is equal to the rate of A from 1 plus the rate of A from 2, but of course I don't have an expression for R2A, I only have an expression for R2C, so I use this expression from the relative rates in order to get that term. So I have R1A minus R2C, which is equal to R1A plus R2A. And I do the same thing for B and C. For B, I am given an expression in terms of A, but I need it in terms of B, so I use stoichiometry here. And then the same for reaction 2, I'm given the rate in terms of C, and I need it for B. Next thing I want to do is group terms. So to do that, I'm going to notice that my rate expressions, I have 2. I have R1A and R2C, and so those show up in various places in my energy balance, but I want to group the enthalpy terms by these rate terms. So first, R1A, if I look here, I have an R1A times A minus HA. Here I have an R1A times A plus 1/2 HB, and that's it. So that's what I have here. And then what I want to be able to do here is convert these expressions into heats of reaction. This is going to be the heat of reaction 1 per mole of A. So reaction 1 is 2A, goes back and forth to B. The product is B. So if I took the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants, all times their stoichiometric coefficients, then I would want my heat of formation of B to be positive, and I would want my heat of formation of A to be negative in that sum. Here, if I go back down to my solution, that's what I have. B is positive, A is negative, so I'm products minus reactants, and what you see has happened here, I've divided everything by the stoichiometric coefficient on A, so I've divided everything by 2, so B enters in with a 1/2 and A enters in with a 1. This is how I know it's the heat of reaction per mole of A. Okay, so now grouping my R2C terms, that's going to give me a plus HA, a plus 2HB, and a minus HC. So that's what I have here, and if I analyze that, that's going to give me negative heat of reaction 2 per mole of C. The reason it's negative is here because I have reactants minus products. And I know it's per mole of C because I have a factor of 1 ahead of this HC. So I can go ahead then, and so I guess I should keep talking about this. This is my heat exchanger term, and then I've moved my this part, which derives from this part, so my sensible heat terms, I've moved that over to the right-hand side of the equation. So now in this piece I'm solving. I want to solve for dt dv. That's the piece I'm going to solve. And to do this, I'm going to take my rate expressions, and I'm going to multiply them by my heats of reaction, and I'm going to fill in delta H reaction 1 here. That's positive, and it's per mole of A. So if I'm given the heat of reaction in per mole of A, so the units I'm given are per mole of A. If I was given per mole of something else, I would have to use stoichiometry to convert. Here I'm given, or I have R2C, and I'm going to multiply that by negative delta H of reaction 2, and that needs to be on a per mole C basis. The heat of reaction that I'm given is in terms of B. So reaction, going back to this reaction, I have 1 mole of C for every 2 moles of B, so that the way I would do that would be to multiply by the factor of 2 divided by 1. That's going to give me the heat of reaction per mole of C. And so if you look in the Python solution, that's what I've done there. But basically this is the expression I get in this first method of derivation. The second way, I'm going to start again from this expression and expand. So I have my sensible heat terms, and then I have my H's times my rate expressions. This time I'm writing the rates in terms of species B. So if I look at, if I consider species A, I'm going to take my leading term, HA, and then I'm going to multiply that by the net rate of A. This term here stays the same. I'm still multiplying by R1A, but now I need to go back up here in reaction 2, and I'm going to pretend that instead of being given the rate in terms of C, I'm now given it in terms of B. So I have, if I want to do the relative rates here, that would be R2B divided by 2 is equal to R2A divided by 1. That means that R2A is equal to 1/2 R2B. So that is why down here I have a plus this time because A and B are both reactants, and I have a factor of 1/2 because the stoichiometric coefficient on A is half that of B. Now for B is going to be pretty much the same as in the last case, so I have to take use stoichiometry and relative rates to write the rate of reaction 1 in terms of B, which I've done here. It's the same as last time. And in this case, now that I'm writing rates in terms of B, I just write plus R2B here. And that should take account, for what's happening to B in reaction 2. And then here I have HC, and I want to multiply that by the rate of C in reaction 2. And I'm pretending again that I have this information in terms of B instead of C. If I had this information in terms of B instead of C, then my relative rate expression would say R2C divided by 1 is equal to R2B divided by -2. So again, R2C in this case would be equal to -1/2 R2B, which is what I have here. So now I'm going to, again, group terms. So this time the terms that I have are R1A and R2B. So I have a grouping for R1A that ends up exactly the same as the last time. I have a grouping for R2B. In this case, my R2B is going to be multiplied by -1/2 HA minus HB plus 1/2 HC. If I look at that, that's the heat of reaction 2 per mole of B basis. So this is, notice there's no negative sign out here because we have products minus reactants. And now the the coefficient on HB is equal to 1. That means that's a per mole of B basis. So if I go down here and simplify that, I can write my expression. Now I would have R1A times delta H of reaction 1 plus R2B times delta of reaction 2. Of course, this is going to be an A basis, and this is going to be a B basis. So that shows, the reason I want to show you that is because these rate terms, they get entered into the expression differently depending on if the species is a reactant or product. That comes from the derivation. So it might be helpful as you're solving these problems to actually write out the derivation. Either that, or it might be helpful to just always say you're going to write the rate or the energy balance using rate laws of reactant species. If you use reactant species, then you want the sign on the rate and the sign on the heat of reaction term to be the same. That means that in cases such as this one, where you're given a rate in terms of a product species, you would have to use relative rates to convert to get a rate expression here, or to at least get the values that you would insert in there. Either way you do it is fine. It's all a matter of accounting. So the key point is to make sure that your equation is doing to the temperature what you think it should be. In this case, reaction 1 is exothermic, while reaction 2 is endothermic. Hence, as reaction 1 proceeds, the temperature should be getting hotter, and as reaction 2 proceeds, the temperature should be getting cooler. So just ensuring that that your rate expressions are going to, or that your energy balance is going to increase or decrease temperature according to the heat of reaction, and if not, go back because you probably have a negative sign error. In this case, we know it's true, so R1A, the rate of generation of A. So when we think about heats of reaction, that's the reaction as going forward. In this case, A is a reactant species, so as the reaction moves forward, the heat or the rate of generation is negative, so the rate of consumption is positive. So when we go down here and we multiply that, so this would be the rate, or that would be a negative number. When we multiply this by a negative number, since it's an exothermic reaction, that would mean that we're increasing the temperature. In this case, R2B, this is the rate of generation of B in reaction 2. B is a reactant species, so this is negative. The heat of reaction is positive because it's endothermic. That means that this is a net negative number, which means it's decreasing the temperature. If we go back up here, we can make the same argument. So this is exactly the same argument as in the last time. Here, R2C, the rate of generation of C in reaction 2, that's positive because C is a product species, and we're going to this time hit that against a negative heat of reaction. Since the heat of reaction is positive, that means negative, the heat of reaction is negative. Hit that by a positive number, we get a negative reaction, or a negative number, which is going to decrease the temperature. So no matter what we do, we should be getting the same result numerically and also the same direction of change of the temperature.